Hi guys. Alright, a few things I want to talk about. We're back on the scope. I have removed the vertical switch, the attenuator switch, and in the process of getting it cleaned up and checking it. It's set down in this area here, so I had to remove the CRT out and its shield, and then there was another set of circuitry here that had to be removed. And then this is the switch. These caps and the resistors in here make up the attenuation for the different settings. This one, the Tektronix, ranges from 50 volts per division down to 10 millivolts per division, so that's what the switch does. But it needs, I got a little more cleaning to do on it. It was pretty dirty in there, so contacts weren't the best. They needed pretty badly cleaning. So anyway, I'm still working on that. But in this video I wanted to talk about some more about the vertical circuits and concentrate on this up here, which starts here and runs all the way around and comes out at this end, and then these two wires here hooked to the vertical plates. And what that is, the delay line. And what I want to talk about a little bit, a very little bit, about how it works and what it's for. Now, if we take a gander at the schematic here, and I'll get it out here. And get me a pointer. Alright, these are the two output vertical amplifier output tubes that feeds into the delay line, which then in turn goes to the tube. We tap off at that point where they feed in, and it comes up and goes to this cathode follower. This is the trigger. What this is the signal that you're putting into an oscilloscope, you put into the vertical. That's where you input at. Well, I need to trigger the horizontal, so we pick that off here. Now that's going to go through some more circuitry and before it gets to the oscillator, and then gets the horizontal oscillator, and then also on out to the horizontal plates. Well, that takes a certain amount of time. For the vertical, we just got a couple, 2-3 sections of amplification here, and if we actually fed this directly from these output tubes here directly to the plates, what would have happened is this would actually, it would go ahead and trigger, but it wouldn't bring the horizontal oscillator ready, bring it in line and ready to sweep across the screen. So it'd still be in its blanking point. See, on the horizontal, that's, you get your line going across the screen, back and forth. Well, when it gets to the full right, then it has to retrace back. It blanks out, so you don't see that retrace, and then it comes back across, blanks, comes back across. If I didn't have the delay line, then what would happen is I would start trying to show my wave on the screen, and I would lose part of it, especially the front edge, because it would be in blanking mode at that point. So instead of having that problem, what they do is they delay it to get into the vertical screen. This delay is long enough that by the time it gets to the vertical plates, ready to show the wave vertically, then the horizontal is set to start sweeping across. It's out of blanking. Now you might wonder, why is that so important if I miss my front edge? Well, a lot of times that front edge, which is also known by rise time, or the rise, can be quite important on when you're measuring certain waves. Say for example, you're measuring something that has, say, a square wave in it, and or something fairly similar to a square wave. Uh, at the very beginning of that, when it rises up and it comes up the screen, it may overshoot. In other words, go up above and then come back down and come to the vertical top part or horizontal top part and move across. It won't be actually square, or it could undershoot, or it could ring. In other words, just get some waves in it. So you need to know that. And if I was not delaying this, then what would happen is I would miss that, and I wouldn't see it. Every time it swept across, that I'd be losing the front edge of that wave. So that's all the purpose of the delay line is so that the vertical starts at the same time the horizontal is starting to sweep across the screen. Now, in this particular scope, and some of the scopes is a little different time, but excuse me, in this particular scope, from this point here, which is the beginning of the delay line, to here at the end of the delay line is 0.25 microseconds. That's how much it delays it. Now, how does that basically do it? Well, what it's doing, it's got several of these coils for each side. You remember, we got two tubes in our vertical output amplifier. These are operating in a push-pull configuration. So in other words, when one's going positive, the other one's going negative. Alright. For each side, here and here, we have a series of coils, and there's tuning caps across those for adjustment. I'll give you some idea what that looks like on the schematic. It's right here. The vertical comes in. This is where the trigger pulls off. You got these coils on each side. We have a variable capacitance in between them. That keeps the impedance the same. In other words, keeps it balanced. This impedance along here and this impedance along here is balanced on each coil by those tuning capacitors. So there's a series, for each side there's a series of 24 coils going up and coming out to here for each side. And consequently, you see all the holes in here. These are able to get to these tuning capacitors or adjustable capacitors. If you have an imbalance, you can adjust it out. Now, the basic nutshell way this works is any type of resistance to current, whether it's just pure impedance or DC resistance, the resistance in wire or resistor or anything, slows current down. If you was looking at a superconductor, which superconductors are a special recipe of certain conductive metals that when cooled down to a certain temperature, they become superconductors. They have no resistance at all. So the current has free travel through them. There's zero resistance in the conductor. In those, current flows, moves along at the speed of light. But in standard wire or resistors or anything else, it slows current down. Now this is operating in on two bases that basically actually come back to the same thing, the way this thing operates. But basically, you got some DC resistance in your wire here in these coils. You know, you can measure these with a ohm meter, and you know they have a certain amount of DC resistance. But remember, we're sending actually pretty much basically an AC signal through here. You're measuring some sort of waveform. And that also creates an inductive reactance on these coils that opposes that waveform. The opposition of the waveform, both by the DC resistance and the inductive reactance, we basically call impedance, that actually slows the current down. Now this is extremely linear, meaning that there's 24 of these coils. It slows it down by 0.25 microseconds. So each coil is roughly about 0.01 and some change microseconds. Each coil drops. And when you add them all up, you come up with 0.25 microseconds. Now I'm not going to get into the actual reasons why any resistance in wiring or any resistance, impedance and everything actually has an effect on current that way. It's beyond the scope of this video. But the main thing here is just for you to understand why this thing's in here. And the main reason for that is so that my vertical starts at the proper time when the horizontal is ready to start sweeping across. In other words, otherwise the horizontal will probably be in blanking, and you'll miss part of the wave. So that's the whole purpose of this. And it is in calibration instructions in the manuals to these scopes. They have they talk about calibrating this, first checking it and making sure it's all right, and then calibrating it if it's not. And on another video I'll talk about that a little bit, how that's done and everything, how you can figure out if you need it. But right now I want to kind of come back to the vertical amplifier and talk a little more about it. So I'm going to lower this down so we can look a little closer into the back side of this, but and probably end up kind of looking at the schematic too. Now, this vertical amplifier, we start off with our input, which then goes to our switch, attenuator switch here. So that's fed in at these 2 points right here. There's 2 points mainly because of those 2 wires hooked to one side or the other side of to a switch, which is for the AC/DC. And what that does, if you switch it to, there's a switch on the front. If you switch it to DC, all scopes will have these, or generally will. You switch it to DC, it's a direct line directly into the switch. If I switch it to AC, then it switches this capacitor in, which blocks, DC. Capacitors block DC, so then you only get AC through. So that's why there's 2 leads on that switch. So anyway, that feeds in. Right here's your input, and there's a AC/DC switch, and feeds into all these switches, wafers that's on this switch. You see here where it says times, hopefully you can see that, times 100, times 10, times 5, 2, and 1. Well, that's these here, these circuits here. These are attenuator details, or attenuator circuits. There's times 100, times 10, times 5, times 2, times 1. They hook into the circuits up in there, where those are at. Anyway, you feed the signal in, you have the switch set to some point, and then it feeds out here. Now, right here and right here you see this little spot in the switch. This says AC only. These are the lowest settings. 10 millivolts, 20 millivolts, and 50 millivolts per division. And when it's switched in those, it's AC only, and that can be fed in there, and that feeds into the preamplifier, which sits right here. Otherwise, it's a direct feed. So if it's not on those lowest settings, it'll feed out here. The reason why they got the preamplifier in there is at that lowest settings, it's not strong enough to actually drive the next set of tubes in here. So they have to preamplify it to increase the strength of that signal. From that point, if we're using the preamplifier, this is its tube here, and it feeds through there and feeds down through this way. Otherwise, we're not on those settings. The preamp is not out, and it feeds through here, which then comes in right here and to these two tubes, these cathode followers, and then to these two. Now, this is an interesting little piece of circuitry. I'm not going to go in exactly how it works. I want to keep this video relatively short today, but if I get comments that want to talk a little more deeply about it, we will. Only one tube in this actually gets a signal. It's coming through here. The other tube comes down through here and hooks to a voltage divider right here. One here and one here. We have adjustment. It says variable attenuator balance. Now what that does is adjusted right, it keeps always the grid at 0 volts on this tube. This tube would be varying with the signal. So if I had an AC signal, it would be varying, but this one would be stationary. What that does, it varies the current through the two tubes. We have on the cathode, we supply 150 volts negative through a 47 ohm resistor, and then the 239 Ks. What this ends up doing between this one held at 0 constant current and this one being varying as the signal varies, will cause a phase shift that is fed into these tubes. These are actually classified as the phase shift tubes because they actually fully do the phase shifting or amplifying of it, and then they feed it out. We're phase shifting mainly because the output tubes we're going to be running at push-pull, and we need to run those at push-pull. So those feed out to the cathode followers, and then they feed into these, and that way one can be going positive while the other one's going negative. What that does is keep the electron beam on there moving in the correct position as it follows the wave. So on one side I may be pushing it away because I got a negative charge on it, and the other side I'm attracting it because I got a positive charge. So if this was going positive and this one was going negative, then the bottom plate here would be negative, and it would push the electron beam away, while this positive one attracts it, and that gives me the proper deflection I need. That's really how they all work. Any type of electrostatic or even electromagnetic, which does a little differently but still works in the same basic principle. One side of your, whether it's your coils, if it's electromagnetic, or one side of the plates will be negative and the other one will be positive, or one will push while the other one pulls. And then when they switch, this will go negative as that sine wave goes through, say a sine wave. When it goes negative, this will start going positive, and then they'll pull the electron beam the other direction. So I need a push-pull signal. If I didn't have push-pull signal, it wouldn't move at all. So now you notice several times in this they talk about CF or cathode followers. Cathode followers are used in a circuit basically as a buffer. And what a buffer is kind of like it allows something to get through, but without the signal being degraded. It separates this grid from the plates of the previous tube and helps try to allow the signal to go through with the at its full force. Now, cathode follower is less than unity gain. It's real close to about 1, but in other words, it doesn't amplify. But what it does do, on the input of its high impedance, but the output's low impedance. If you got low impedance feeding back into this tube here, the cathode's always low, so I have a low impedance feeding into a high impedance here. I don't drag that signal down. But if I was running that directly from the plate through a coupling cap or something and over, for one thing, the coupling cap could cause me some problems at certain frequencies. This has got to look at anywhere from DC all the way up to a good 10 megahertz, because the 10 megahertz scope, it actually will go higher than that. But the other thing is too, I could have some degradation of the signal because of the impedance is still fairly high on the plate. It's not as high as the grid, but it's fairly high on the plate. So I've got the plate coming out the first tubes here, out of these tubes, and feeding into a grid, so it's a relatively lower impedance. It's definitely a lower impedance than the grid, so it makes an easy passage, doesn't load it down, and then it feeds to the cathode follower, which again, coming out of that cathode follower, this will be about the same strength because they're close to unity gain, and it'll feed into the high impedance here, again not loading it down. So I can feed a fairly weak signal in here and it will go through. The 100 millivolt per division signal in here, and it'll just amplify it. I won't lose much of the signal. That's why they use the cathode followers. And there are buffers is another name for them. So anyway, that's about all I got to say about this. Again, if you want more information on how this thing phase shifts, a little more detailed here, I can do another video on that. If you want to know, want something to a better understanding exactly how that delay line works, or any delay line, or just resistance slows current down, I can do a video on that, a dedicated video on that. Otherwise, any other information on this, I'll get the switch cleaned up. Now the horizontal seems to be pretty good shape. I looked at it under bright light, but it was the vertical that there were some points on it that you had to kind of mess with it to get it to make contact, and it was kind of pretty blackened in there. So I'll get it cleaned up, remounted. I've checked this cap for leakage, and it seems to be good. No leakage up to the highest setting. I can check it. The electrolytics, I have at least the main ones in here. I've disconnected all of them and went through and checked them for leakage, and they're doing good now. They seem to reformed up pretty nicely. So at this point, I think what I'm going to do is get everything kind of cleaned up. You get the switches cleaned up. Some of these pots on here just need a little lube on them. They seem not to be scratchy. They're pretty well sealed, but they're a little stiff, so I'll probably pull the knobs off and put a little bit of lube down the shafts to get rid of the stiffness and get it all back together. Oh, one other thing. I had a question on there about the scope tube, and it was asked if it had a burn-in. Yeah, it has several of them. There's a little bit here. This is the main one here, one here, and actually I don't know if you can see it on the camera or not, but it comes flat and then there's some squiggles here. So they actually had it on for quite a while, probably the intensity up fairly good at one time, and on way too long with that intensity high, and it actually burnt some of that in. But even on this worst place, when I was playing with it, it still shined up pretty decently. But I'm not as concerned. These are not that hard to find tubes. But also where I got this scope from, which I'll be going up here in a couple days back to that place. He has some scope CRTs, new old stock ones, and I'm sure that there's probably one of them is one for this. Anyway, there's your oscilloscope CRT. There's the plates. That'd be the vertical plates right in there. Horizontal plates are back this way. It's kind of hard to see them. And the rest of the other connections. And your high voltage here. So yeah, it does have burn in, but it's still usable. And if they don't have one up there, then I'll probably just put a search out on eBay. But I've seen them on eBay before. Scope CRTs are not hard to find. So anyway, that's about all I've got on this. Again, if you want more information, just leave me a comment and we can run some more information on it and stuff. And on more individually how some of the circuits work, how the delay line, or how anything gets delayed, and resistance, impedance, and so forth. So if you like the video, give a thumbs up. I do read your comments, and I thank you for them. There's really only just a couple questions in there, so I usually just try to answer them on the next video. But if you do want to see more on that particular, the vertical, the delay line, then just leave it in the comment and we'll do a video on it. So until next time, thanks for watching, and I'll see you guys on the next video.